talk through the vFunction Architectural Observability and Automation platform. To begin, we'll focus on a single Java application. We'll see how an architect can use the dynamic analysis and AI capabilities of the platform to automatically identify the domains of the application and the relative level of technical debt in the application. Next, we'll show you how to interact with the platform to refine your view of those domains, to reflect the architecture you want to set as the baseline. Then, we'll demonstrate how the platform uses AI to recommend modernization to-do tasks for your developers to mitigate the architectural technical debt. Finally, we'll show you the same application observed after a future release and how the platform tracks the architectural drift, including areas where technical debt was remediated and other areas where it accumulated. To close the demo, we'll illustrate how enterprise architects with responsibility for potentially hundreds of applications can get a bird's-eye view of the entire estate, visualize how architectural technical debt is trending across the portfolio, identify where the bright spots or trouble spots are, and then drill into any application or a group of applications for further exploration. Identify domains using dynamic analysis and AI. We are looking at the vFunction view of the architecture of an order management application. The vFunction platform automatically identifies domains within the application, based on data science algorithms. Green spheres represent domains that have high class exclusivity, while red spheres represent domains with low class exclusivity. The higher the exclusivity, the better the architecture, and the less cross-domain pollution exists. The dotted lines between domains represent calls between them, and the solid lines represent shared resources across these domains. Resources may include files, beans, transactions, database tables, and the like. The system allows the architect to refine the view of the domains and change their boundaries. Refine a baseline view of the architecture. Let's note two such examples where we modify the boundaries of domains. In the first example, we see the shipping service domain is red, and it has a dependency on the modify fulfillment domain and the shipping controller domain. Let's merge the two shipping-related domains into a single shipping domain by simply dragging and dropping one sphere on the other. Similarly, in the second example, in reviewing the product domain, we see that the exclusivity of the dynamic classes is 66%. Looking at the classes, we find the inventory class is in two domains, although it clearly belongs to the inventory domain. Let's find the right place to add an entry point into the inventory domain, creating a boundary between the domains. Once the analysis is finished, we can see that the exclusivity has improved. After these two actions, a modularized view of the architecture emerges. Point out tech debt and generate to-dos to resolve it. Now let's look deeper into the architecture. We see that the platform exposes two high-debt classes. High-debt classes are the classes that contribute the most to the complexity and entanglement of the domains, and will require some manual refactoring, either by splitting them or by changing their design patterns. Clicking on one, we see that it has many dependencies, and that it requires refactoring. We'll add this to our to-do list as architectural technical debt that needs to be fixed. An important aspect of architectural observability is the interaction between the business logic and the data layer. Let's look at the resource report and see how the database tables are used from the various domains. Here we see, for instance, that the order line database table is used in the context of three domains: Let's fix that. Clicking on the Modify Fulfillment domain. Looking at the non-exclusive resources and selecting the order line database table, we can jump to the right place in the call tree. We see the sales order entity class, which was added to the common library by the platform. Let's remove it from the common library and add it as an entry point to the order domain. Once the analysis calculation is complete, we are able to see the added call between the two domains, and that the order line table is now used only from two domains. We will add a to-do item to refactor the code and make it exclusive later. Finally, you want to look at dead code. We have the D badge, signifying dead code, on the product domain and on the app itself. Looking at the product domain, the dead code class is the Modify Fulfillment Service class that can be removed from the code. Under the application, we will see all the classes that were not executed at all during the learning or dynamic analysis phase. Now, after establishing a business-oriented, modularized view of the app and listing a few to-dos for the development team, we can set it as a baseline and measure architectural drift against it. We first click on Configuration to set the baseline, and then configure the architectural notifications and thresholds we want to monitor. Then the plan, and lastly, the schedule of the ongoing observation. Tracking architectural drift can also be triggered through the CI/CD pipeline, through a script that invokes the dynamic analysis on demand. Observing drift in a future release, positive remediation, and negative accumulation. Let's see how this app looks after 2 weeks. First, we can see 3 architectural events that occurred. The first one shows a singleton bean that was previously used exclusively from one domain, but is now used by 2. Secondly, an alert that the domain exclusivity dropped on 2 domains. And a third event that a new domain, the customer domain, was found, indicating new functionality was added to the application. Looking at the measurement itself, we see that some of the issues we identified 2 weeks ago have been fixed and no longer exist. For instance, the high debt classes were refactored and the list of high debt classes is now empty. However, new to-do items may have been added due to architecture drift, due to the new functionality added to the application. This has been a short architectural observability cycle. From the initial view of an application's architecture, refining its view, generating to-dos to fix some issues, and then measuring architectural drift against that baseline. Now that we understand how architectural observability is used iteratively throughout the software development lifecycle, let's take a look at the portfolio view. We start with the assessment dashboard, where we can view the entire assessed portfolio. Filter apps by level of tech debt, tech debt trending, tags, sizes, and technologies. Let's look at a specific app assessment report. We can see the level of technical debt represented as the percentage of dollars invested in tech debt every sprint. Another view in the report shows the tech debt of this app on a relative basis to the rest of the portfolio, represented through risk and complexity metrics. There are additional metrics in this report, including aging frameworks, total number of classes, and the trending of tech debt. Let's jump into the portfolio view. Here we can see some onboarding metrics. For example, how many apps have been assessed, how many have gone through learning, as well as ongoing observability metrics, like the aggregate number of events and their types across the portfolio. In the lower tiles, we can actually see the aggregate architectural posture, which includes the technical debt level across the portfolio, and the architectural complexity that has direct correlation to the amount of effort needed to address the technical debt. This is a valuable metric for the chief architect to measure and monitor architectural tech debt at the organization level. If the architect chooses, he or she can drill into the to-dos in any or all applications. If we expand this portfolio dashboard, we can actually drill into any application of our choice, manage its observability metrics, and monitor its architectural events. These architectural observability capabilities are foundational to any modernization process or initiative at any organization. Regardless of where you are in a modernization journey, vFunction Architectural Observability Manager gives you the continuous ability to see, measure, and fix your technical debt at a pace that works for your application teams.